Okay. We also deal with buoyant forces in this section. So buoyant forces essentially are based off of the whatever liquid is displaced. So just to kind of clarify, so say I have a person with this beach ball here, and they're putting their weight on this beach ball, okay, to try to push it underneath the water. Um, this is just kind of like an example of what that model would look like. This is sort of a cube that would sort of be floating under the water, so it's got some density that might be somewhat close to water, right? But it's not dense enough to sink all the way to the bottom. So one thing about this buoyant force is we model, like we talked about before, we can set the mass equal to a density times a volume, okay? So we can set this buoyant force equal to rho v times gravity. But this rho value is actually the density of the fluid that is displaced, okay? So it's not the density of the object itself, it's the density of the fluid that is being displaced by the object. And that's going to give us this B, which is a buoyant force, basically. So it's that force that's that's pushing um, uh, back up, essentially. And we'll see kind of some examples in the problems where I think it'll make more sense. This one is intuitively a little bit weird. Okay, so this is kind of the relationship here. So the volume of the fluid over the volume of the object is equal to the density of the object over the density of the fluid. So this is like one relationship that you can kind of use to solve your problems. So again, sorry, a lot of equations in this section. Okay, so yeah. So if the object is totally submerged, yeah. So if the object that is submerged has a density that's less than what it's submerged in, it experiences a net upward force. So like if I'm pushing something underneath, or if something's underneath the water, but it has a density that's less than water, it's trying to float, basically. So like this piece of wood would be pushing up, right? But a totally submerged object that is denser would be sinking, basically. So the buoyant force can, or not, the net force essentially can vary, and it'll be dependent on the density of this this object. But the buoyant force is just based off of this displaced fluid. Okay. So that might not make sense right away. We're going to do some examples. We kind of talked about this a little bit before, but I want to intro both of these ideas before we kind of look at the example problems because they'll both be important. So this is an example of a barometer. Okay, so we talked about this equation before. Okay, and for this barometer, this is just like mercury in here, and it is mercury that's affected by an outside pressure. So if I think about this outside pressure kind of pushing on this, we're modeling this as P naught because we're saying like this is the surface where the pressure's acting. And inside the barometer, this is like a vacuum. So there's this outside pressure from the surface that's forcing this mercury up. And so in order to measure the external pressure of the environment, okay? There are two different terms in a problem when they ask you to find pressure. They might ask you for the absolute pressure or the gauge pressure. The absolute pressure is this P value here, and the gauge pressure is the difference between this P minus P naught, okay? We could say this is like this kind of delta P. Okay, so for example, in this case, the P naught, okay, would be equal to this rho GH for mercury, okay, where the density of mercury, so mercury is the fluid that's being displaced upwards, okay? So the height, if we were say, try to figure out the height that this was being displaced just for a normal barometer, we would be able to model this as 0 because we're modeling the internal part kind of as a vacuum, so there's no pressure as it's going up. And then we could figure out the height of the mercury and use that to figure out this this external pressure. And that's kind of how barometers work. Based on the height of that line, we can figure out the external pressure of an environment because we know the density of mercury and whatever the gravitational force is. Okay. So this one's a little This example problem is a little bit long. I will go ahead and let you guys read it if you would like to try it. I'll go ahead and stop and record it separately.